My pleasure to introduce Thomas Liljeberg. Thomas is Senior Director for Silicon Photonics Products at Intel, where he's responsible for the integrated and co-packaged photonics product and technology roadmap. From 2004 to 2015, he was at Source Photonics, serving in various roles in product management and R&D management, most recently as Executive VP of Product Line Management. And prior to Source Photonics, he was with Agility Communications. And Thomas holds a PhD in electrical engineering from the University of California, Santa Barbara, and an MSEE from Technical University of Denmark. Thomas, thanks very much.
Great. Thank you, Rob, for the introduction, and thanks to the organizers for the opportunity to speak here today. If you looked at the program, I'm filling in for Robert Bloom, who unfortunately could not make it today, but I'm glad to get the chance here to talk about our effort here in this area. I hope you can all see my screen right now.
Yep.
I'm going to start. It's a little bit along the lines of where Manish was going, and I'd like to look at the chart here because this is something that we've in one form or another looked at least as long as I've been working on silicon photonics at Intel now 6 years or plus, and really looking at sort of where does the technology go, what's the roadmap for integration, and how we view our position here. And of course, it starts to the left, and this is where what we've been working on in the Ethernet data center networks with pluggable optics, and then there's a rich and comprehensive roadmap there. It's not going away anytime soon, from now at 800 gig and beyond. And there's a large volume and that's being built and in the field now, 5 million plus units. So on the back on that, we've built a healthy infrastructure and high volume capability that now can be leveraged into sort of the next step. It's also clear, as even though we build with these pluggable modules, as Manish pointed out, we're increasingly facing challenges even in that application with pluggable. And Manish looked at how many of the links are exceeding the BLOS budget. Another way of looking at it that I like to think of is if we think about moving bits from a switch to a switch across hundreds of meters, how much energy are we spending on the non-value add 12 inches, first and last 12 inches just to get to the front plate? And as we move up in speed, more and more is just wasted on that, both in share of the power budget, but also in total watts. So the answer is, like Manish said, let's put the photonics inside. And the way this is conceived, at least in first generation, is really miniaturized. There's no repartitioning or sort of changing the functional blocks, but let's move the transceivers inside the package, make them smaller, use less power, but really tap into and leverage the existing ecosystem and multi-source environment, and that's one way of doing it. And with that, we can get some meaningful power savings while still interoperate and not reset the whole thing. But there's some limits to how far that can be taken. But that's certainly something that we're working on, and I'll show 1 or 2 slides on where that stands and where we think that's heading. As we take integration further, and now we're getting into what we think of as XPU Optical I/O or compute platforms. We're now moving closer to the value-add digital logic, and whether that's an XPU or an FPGA or any kind of SoC that needs high bandwidth. We're unconstraining ourselves, as say, from past decisions on Ethernet or past optimization points, and what's the best we can do, and how do we deliver the most bandwidth, the highest density, and the best power efficiency for that. And I'll show our thoughts on that, where we think that is heading, and on our work in that area. But first, on the Ethernet switch, showed various versions of this before. We build a system in order to learn and to understand constraints and capabilities. So this is a fully functional live traffic Ethernet switch with co-packaged optics, and it's built around a 12.8T switch. We designed for 25, but 12.8 was what eventually made it in there from availability. Co-packaged with these 1.6 terabit per second engines, or parallel optics, so you can think of it as 400 gig DR4s, socketed as we talked about to have that abstraction or standardization point, which is seen here to the right. We have 4 of these engines around the switch here with the retention hardware here. heat pulled out to heat pipes to heat sinking out here. We've removed the big heat sink that takes care of the 300 watt of switch in there. And then the same sockets accommodate flyover cables, so we can bring bandwidth to the front plate for pluggables or for back cables or for cover back planes, however you want to design the system. And a lot was learned from that, and as I think we think about it, that's we're not taking the learnings from what we did here into the product direction for CPO, for Ethernet switches, but also there's learning in packaging and devices that will benefit when we look at the compute platforms and the optical I/O for that purpose. But even here as a first iteration, we saw something that looked like 40x bandwidth density versus a pluggable module and 30% power reduction in this first iteration here. And I think that's promising, and that shows some of the potential for what we can achieve with co-packaging. The core of these optical engines, photonic engines, with this 1.6T transmitter chip, and I kept that in here because it really highlights some of the benefits and opportunities for high degree of integration. So what we're showing here is the 1.6T transmitter chip. Like I said, it's 16 channels of 100 gig parallel optics. So we have, if I follow the photons around from a laser array, redundant lasers for reliability, through a setup of 2x1 optical switches to pick which of the redundant lasers we're firing up, 100 gig microring resonator modulators for data encoding, and then around the edge here to mode converters and deep grooves, and that's really designed to enable efficient, scalable assembly, ideally with passive alignment into these deep grooves here. So that's what the transmitter looks like, and that's what a lot of the device learning here is going to leverage into subsequent developments for this. What is coming into a product is really for next generation 3.2T Photonics engine, and we're now leading with the sort of lead configuration here is a WDM version, so 8 ports of 400 gig FR4, still in socketed, say self-contained transceiver arrays, consistent with the statement of not repartitioning and still leveraging the existing ecosystem here. We're adding the laser array onto the chip, and also MUX and DMUX. So again, we have a fully self-contained optical system here, and I think it matters not only for sort of performance and power, but also for manufacturability and cost. So because the laser is on here, because all the MUXes and DMUXes, everything is on here, we can actually test this at wafer level and really implement the concept of known good die into the optics space here. And there's no back end or assembly for the optics that we have to go through. We're making some advances in packaging versus our demonstrator to achieve 4x improvement in bandwidth density and in some signal integrity. But really, it's all directed at aligning with the emerging standard in OIF and elsewhere. And we're committed to really track that influence and track what happens at OIF and elsewhere, so that this truly becomes a part of a healthy ecosystem. But the landing here is a 3.2T engine aligned with the 50T switches in 2024 kind of time frame. So that's what we're seeing happening on the network side. And I think the other part of sort of parallel was when I talk about what happens when we bring things even closer and we're unconstrained from these ecosystem and legacy issues of networking, and try and optimize for these specific applications. So what we've been working on for a while now is this we call optical I/O attached to an XPU, and this is kind of the cartoon version of this concept here. So we have the host IC, generically an XPU here that's co-packaged using, in our case, an embedded bridge to really leverage the maximum density and power efficiency on the in-package interconnect here. And then this optical tile consists of a single electrical IC that has driver, CDR, TIA, some control circuits, and then the photonic chip with the lasers and detectors and MUXes, DMUXes, and so on. So that's built as a single stack fiber attached, and then I said co-packaged into the embedded bridge here. where we think we can take this sort of in first Gen 1 and Gen 1.5, it's a very high bandwidth of a terabit per second per fiber. We can reach hundreds of meters. We don't think that's the sweet spot, but as we all know, once you paid the power overhead of converting to photons, we can go, it's cheap to go far. The sweet spot is probably 10 meter, few tens of meters, but the capability is certainly there for more. Shoreline density, we have line of sight to something that's about 4 times better than what we think is the right reference in this time frame, which would be PCIe 6 port. And that's achieved by using this parallel high density interface through the embedded bridge in the package. Again, energy efficiency in line with or slightly better than PCIe 6 port, but with the longer reach, obviously, and the high density is the benefit. And the goal and the expectation is that we can do all this with a minimal incremental latency relative to a copper port. So that's kind of what we set out as its goal, but the goal informed by line of sight to landing these metrics here in a manner that's consistent with a product and high volume manufacturing. So what does it look like with the optical plane? So this is the chip that we've built and that is intended to achieve what we saw on the previous page. It's realized as 8 fiber pairs, each running 8 wavelengths at 64 gigabit per second NRZ. I think maybe that's worth a discussion at some point on what is the right format, what is the optical interface. We picked 64 gig NRZ because we want to go as fast as we can while staying at NRZ. It lines up well with PCIe or CXL type of infrastructure. We think NRZ is where we'll get the right performance in terms of power and also latency. So again, if I walk around the die here, along with the photons, we have a 8 wavelength laser array. See performance here on the bottom right. So we're pretty pleased with what we get there. Very reproducible, controllable channel spacing, very uniform performance across the wavelength, including over temperature, which is not shown here. That gets muxed and then split into eight lanes feeding the 8 fibers. Each lane runs down a cascaded set of rings, modulators, encoding the data on there. And then through SOAs, again, mode converters and V groups onto the fiber, coming back through amplifiers, and then we use again ring modulator or ring resonators for demux purposes. We also have some, not seen here, but there's structures there to manage polarization, so we don't have any need for control or prior knowledge of the incoming signal here. So it's really intended to be, again, a fully self-contained optical system here that can exist in a true field deployment. So that's what we've built this and we're looking at that now. We're developing the packages and looking at how to attach that to different options for host silicon and have some plans in that we can maybe be able to talk about in another setting. I think the last thing is in terms of what can be achieved and where are we ready in terms of devices and technology, but we also want to make sure that the path we go down is one that's scalable and we don't have a single generation solution here. So we looked at where can we take this, and this is not intended to by any stretch be a disclosure of product plans or anything even close to that. But we're just looking at, we have different vectors to improve our bandwidth and performance here. We can add more wavelengths, so 8, 16, 32 is certainly a scalability path. We're building a 32 and 64 gig NRZ right now. We have in lab, and I think we've published performance consistent with 128 gig NRZ for the same type of ring modulators. We can add fiber count, and then there's a one-time benefit of using 2 polarizations to this. So we think that without inventing new physics or dramatically change the architecture, we have a nice runway of doubling this, maybe 6 times or so the bandwidth of an IO tile. And I think that's the sort of the last checkpoint we had on that. So that highlights where we're seeing what we're working on right now and what we see as the initial intercept for these compute platform optical interfaces. I don't know how I'm doing with time, but I'll stop here and leave some time for questions, hopefully.
That's great. Thanks very much, Thomas. And I'm sure we'll come back to some of the performance metrics that you posed as targets here when we get to the panel discussion a bit later on. We do have one question that came in on the chat. Could you comment on the laser heater on slide 4, please?
Slide 4. On the laser
heater, I think and where you bullet number 2, it says integrated heaters.
Yes. So that's on the switches. So that's to align the switch and make a selection between the 2 lasers in the redundant pair. So the transmitter is realized as full 1-to-1 redundancy per channel. So that's why we have a 2x16 array here. And then the integrated heater here is to control the switch here to pick the laser that we want to activate.
Got it. Great. Well, thanks again, Thomas. Very interesting talk.
Thank you.
Okay, so it's my pleasure to introduce.
One quick question. It's sort of generally applicable to a lot of people, though, which is what granularity does everybody want, right? So it's great you're going to what, 64 terabits for fiber.
Yeah.
What do the architecture guys really want? That sounds like an awful lot of data going in one direction. And if that fiber were to break or something, then obviously it's both. Yeah. So what is the right granularity? Is that beyond it, or?
I don't think there is an answer. And there was a little bit of a cop-out comment on that slide saying that the exact scaling, when do we add wavelength versus when do we add speed or fiber, really depends on considerations like what you bring up there, John. I don't think there is a clear answer. There will certainly be cases where you care a great deal about radix and you would want to add fibers. And there may be other cases where it's more important to absolutely do the best you can in density and stick as much you can on a single fiber. So I don't want to sort of judge what the answer is 6 years from now, but I think that there's multiple vectors to go about it here, and I think that's the point, that we can scale the bandwidth along different approaches.
If I could ask one other question, it seems to me like your density is at least 4 times higher than, say, the 100 gigabit transceivers that you sold before. So does that roughly correspond to 4 times cheaper price per bit, sort of? I mean, because in the end, isn't silicon area by far your dominant cost?
Yeah, there's absolutely a very significant improvement in what the cost is if we try to project out in maturity and volume. I'd probably hesitate to put a specific number right now, but I think I don't think that the pluggable module cost is a very good indicator for what co-packaged optics should cost once it's mature and in volume. I think it's a discontinuity in that curve.
Okay.
It's hard, and day one is difficult, and you know how it is coming up these curves on yield and learning and all that. But what we care about is what does it look like in maturity when we've shipped a lot of these, and I think that's a completely different picture than a pluggable module.
We had one more comment that actually our next speaker made. Chris Cole raised the question on the OFC 2021 demo. The density improvements listed as 40x. And his observation is it looks like it would be difficult to even double the assembly. I don't know whether you could comment on that, Thomas.
Yeah, the 40x, I think, is just taking what's the size of a pluggable module and how big is our 1.6T engine and normalized to bandwidth. And then the OIF spec is a little bit smaller than what we had in our demonstration at twice the bandwidth. So that's the slightly better than doubling or in the next iteration. But I mean, we can argue what the right reference points are and all that, but certainly what's clear is that it's a very significant increase in density that we can derive out of this.
Yep, very good. Well, thank you again.